All right, so this video is going to be the first of three about titrations. Um, we're going to do one with strong acids and strong bases, one with weak acids and strong bases, and one with weak bases and strong acids. Um, hoping shorter is sweeter. Um, we're dealing with strongs. And so anytime you are having a component that is strong, in this case both, you need to deal with stoichiometry. We need to figure out which one of the two is limiting, and then determine whether we have more hydrogen or more hydroxide present after the titration is complete, account for the volume of the mixture, and then use our pH equations to determine what the pH is of that ion, whether it be the hydrogen or hydroxide. If both reactants, both the strong acid and the strong base, are equally consumed, they're both limiting, then the only component that we will have in our mixture that has any acid-base quantities would be water. And water, being neutral, would have a pH of 7. And you don't have to go any further than that. So this is an example. You've seen graphs like this already this year where when you are starting with a strong acid, your pH is going to be very, very low. You will notice as opposed to the buffers, basically it just stays low until you reach the equivalence point, the point where the moles of the acid and the moles of the base are equal. They're both limiting. When you reach that equivalence point, your pH drastically increases. You'll notice right around 50, if you look at the data points, you'll see that at 49, it was at 3 of a pH, and at 51, it was at 11. So it jumped up quite drastically here, and now it's going to stay basic the rest of the way throughout. So with strong acid, strong base titrations, you're either acidic, or you're basic, or you're neutral. There's not a whole lot of give. And you're going to be very acidic or very basic. You're not going to have any in the middle ranges. So this problem has 4 parts. We are going to add different amounts of acid. This one's going to be the opposite of the graph you just saw. We're going to be titrating the base with acid. And we have strontium hydroxide. Remember, that's got 2 OHs present, so we need to keep that in mind with its concentration. It's being titrated with 0.1 molar hydrochloric acid, so that's our source of hydrogen. And we want to know the pH after we've added different amounts of HCl. In this first example, we're not adding any HCl. So the only component that's present that will have any effect on the pH is the strontium hydroxide. So that would be the reaction between the two. And if we were going to look at it from a net ionic perspective, it would just be the hydrogens and the hydroxides influencing the reaction. We don't have any hydrogen present this time, so we're just going to focus on the strontium hydroxide, which means we just need to find the pH of that strong base solution. Now, POH is an easy way to figure out the pH of strontium hydroxide since OH is present directly. But I want you to notice that it's 0.2 molar SrOH2. And since there are 2 OHs present, the hydroxide concentration would actually be twice that. It would be 0.4. Okay? When we take the negative log of that, we're going to go out 3 decimal places and get a POH of 0.398. We want the pH, so 14 minus that would give us our pH value, 13.602. So if all you have is a strong acid or strong base, you just figure out the pH how we've done it previously. When you have both strong acid and strong base present, like you do in part B, we've got to account for the stoichiometry. We've got to look and see how much hydroxide we have, how much hydrogen we have, which one we run out of first. So we're going to set up an ice chart, even though it's not going to be a true equilibrium, just because it's going to make it a little easier to keep track of both the hydroxide and the hydrogen. Um, we need to have moles as opposed to molarity since our concentration will have a different number of particles depending on the volume of that solution present. So to find the hydroxide, we would take 0.1 times 0.4, since again there's 2 OHs present, and we would get 0.0400 moles. With the hydrogen, we would take 0.2000 liters times 0.100 molar of the HCl to get our hydrogen concentration, 0.02. Water is not going to influence anything, so we don't have to worry about it. Because these are present in a 1-to-1 ratio, we will see that hydrogen is in a smaller amount, so it is our limiting reactant. So we're going to consume all of the hydrogen, and with that, we're going to consume part of the hydroxide. The hydrogen is going to go down to nothing, while the hydroxide is going to now have 0.0200 moles present. As that is strong base, just like we did in part A, we're going to find the pH using the moles of hydroxide, but we need to account for the volume that's present in the mixture. We don't just have 100 mils of strontium hydroxide, we now have that plus the 200 mils of hydrochloric acid, so our new volume would be 300 mils. So when we find the pOH, again, we need a concentration. We're going to take the 0.02 moles of hydroxide and divide it by the 0.3 liters, 300 liters, to get its concentration, which is now at 0.0667 molar. The pOH would be 1.176, so a little higher than what we saw on the previous slide, but the pH is still going to be very basic, 12.824. In our next example, again, we have strong base and strong acid present, so we're going to set this one up just like we did on the previous slide. We don't have just one of them, we have both. So we had, again, 0.04 moles, zero point 0.4 times 0.1, and we have 0.4 times 0.1 moles of acid. The acid amount's changing this time because if we look at part C, we see that we had 400 mils of the acid, whereas the amount of base did not change. So that's why the moles of the acid are increasing, because we're titrating it. We're adding more of the hydrogen ions. If you look at both of these, they're both limiting. We have equal amounts of both. So this would be when we're at the equivalence point. We have consumed all the hydrogen and hydroxide that we had present originally. So the only component that has any effect on the pH is water. And since water is neutral, our pH would be 7. I wouldn't care if you wrote 7 or 7.0 or 7.00. It really doesn't matter. I just kept the decimal places because of what we had in our moles to begin with. Finally, in part D, we are going to switch limiting reactants because we are adding an excess of the hydrochloric acid. We now have 600 mils of that hydrochloric acid present. We still are going to have the 0.0400 moles of hydroxide, but now we're going to have 0.0600 moles of hydrogen ions, 0.6000 liters times 0.100 molar. Our smaller amount is the hydroxide, so that will now be our limiting reactant. We will have consumed all of our hydroxide, and we will have 0.0200 moles of hydrogen ions remaining. We need to find the pH of the hydrogen ions that are present in our mixture. So we account for the fact that the hydrogen ions are dissolved now in 700 milliliters of solution, the 100 milliliters of strontium hydroxide, and the 600 milliliters of hydrochloric acid. And when we divide those two quantities, we get that the concentration of hydrogen ions is actually 0.0286 molar. When I take the negative log of that value, my pH has dropped drastically because now, again, I'm in a primarily acidic solution, 1.544. So that's the end of the first titrations video, and the next one will follow shortly.